I'm going to share my screen on this machine. Okay. And from current screen. So this, for anyone who's checking in on this recording after the fact, this is just going over the mechanism of ozonolysis. So let's take a relatively straightforward example and just go through this again. So is this an okay example?
Yeah, I think so.
Okay. So it's the same principle no matter what. No matter what the example is, it's exactly the same steps in the mechanism. And a lot of people are saying, well, I know how to get to the product. Not sure what's going on in the middle. So we're going to talk about what goes on in the middle. So I'm going to run out of slides apparently. So I'm going to, as you can see, this is really, really slick production values. Okay, so ozone looks like that. And what we're going to do is we can attack either end of this double bond with the negative charge on the oxygen. We don't want that negative charge on the oxygen. We want to stabilize that. What we also don't want is we don't want a positive charge on this middle oxygen there. That's pretty bad. So I'm going to use a lone pair on this oxygen. I'm going to attack this nearby carbon. It's probably actually going to be the other one because this is less electrophilic because it's got dye substituted. So it's kind of the negative side. No, what am I talking about? No, this is good. Good. This is where you would have the delta plus, and this is where you would have the delta minus if you were to split that double bond. So what we're going to do is we're going to attack that carbon. Once we attack that carbon will be making 5 bonds. That's not allowed. So we're going to break one of the bonds on that carbon, and we're going to use the double bond to attack this other oxygen. And the reason we're going to do that is by doing that, we can release 2 of the electrons in one of these in the double bond up here to the other oxygen onto that middle oxygen. So what do we get out of that? Well, we get a 5-membered ring. And everything is neutral. This was negative. This oxygen here was negative, but now it's making 2 bonds. It's neutral. This oxygen here was positive because it was making 3 bonds. Now it's making 2 bonds. It's neutral. Everyone else is neutral because this carbon's made a new bond and lost a bond. This carbon's lost a double bond but made a new single bond. This oxygen has made a new single bond and lost a double bond. And everyone else is, we've discussed that in excruciating detail. Okay, now what we have here though is this system is really, really, really unstable because we have 3 oxygens all in a row. They're all making oxygen single bonds. That's really bad. Not happy. And so this can fall apart. And when we're thinking about how we want to make this fall apart, we want to make it fall apart to make oxygen carbon double bonds because that is a stable double bond. So what I'm going to do is I'm going to use a lone pair on this oxygen to make a new oxygen carbon double bond. But if I do that, my carbon is going to make 5 bonds. That's not allowed. So it needs to break a bond. What does it break? Well, if it breaks this carbon-carbon bond, to make an oxygen carbon double bond, which is the whole point, I have a really good bond to break because this oxygen, I will need to now break a bond to this oxygen because it's going to make too many bonds. It's going to use too many orbitals. So I'm going to break one of these oxygen single bonds, which is kind of the whole thing. We want to get rid of these oxygen single bonds. Okay, so we follow that logic through. We get that. Now, this does not look stable, and that's because it really, really isn't. We've got that negative and we got that negative oxygen, positive oxygen thing we started with ozonolysis. But if you note and you're looking carefully, now we only have one oxygen-oxygen bond. We've gotten rid of the other one. So we had three oxygens all linked together in ozone. Now we have two. This is better than ozone. This still really isn't very happy. Now it can go straight back to where it was. It can do the reaction backwards. Or what we can do is what I'm going to do is I'm actually just going to rotate one of these molecules. So I'm going to keep this guy the same. And I'm going to turn the aldehyde on the other side on its head. And now we know that ketones and aldehydes are polarized such that the carbon here is quite positive. We've seen lots of things attack those carbons when we were talking about carbonyl chemistry. And so we got a good nucleophile in the O minus. It attacks the electrophilic carbon. Sweet. That could push up and give me an O minus here. But instead, it could attack the other carbonyl. And so we have carbonyls attacking carbonyls. And when we do that, this carbon would make 5 bonds. That's not allowed, so we have to break a bond. And we break the double bond onto the oxygen. What happens when we get there? We follow all the arrows. Is again, we have dealt with our charges. Now, if we're comparing A and B, we can see that they're quite similar, except B has fewer oxygen-oxygen bonds. So B is lower in energy. So although we have to go through this high energy C state, we end up in a lower energy state. So A will go to B eventually. This this is our secondary ozonide. This is our primary ozonide. And an ozonide is a construct of a double bond with ozone. And primary is because it's the first one, secondary because it's the second one. Not primary, secondary in terms of how many things are attached to carbon. Okay. Nothing more can happen there. That's about as good as it can get until we add that extra nucleophile. That can be dimethyl sulfide, that could be triphenylphosphine. For fun, I'm going to use dimethyl sulfide. It's a very, very weird definition of fun. And so obviously nothing happened with the secondary ozonide. So if nothing happened with that and I need to add a reagent, I expect my reagent to be in the first step of the arrow pushing. Otherwise, something would have happened already. This is actually kind of a good general rule, especially when you're randomly flipping screens. There we go. So I am going to use the sulfur to attack the oxygen. That's weird. Oxygen is not an electrophile generally, but oxygen, when bound to a really good leaving group, is. It's just oxygen's never bound to a good leaving group. Oxygen is the leaving group almost always. It's never attached to one. In this case, it is. It's attached to another oxygen. So I'm going to draw an intermediate. I'm not sure this one exists. That's why I put in brackets, and that's because, and the reason I'm not sure it exists is because I think everything happens really, really quickly in one step. I don't think there's kind of multiple steps here. But I just want to sort of keep track of the charges just for a second. This is not a transition state. This is a valid Lewis structure I've drawn here. It's an intermediate. I'm just not sure it's really there of all the reactions, all the electrons flow at once. Because now when we've got this, we can see that, remember, I like carbon-oxygen double bonds. Let's make one. If I make that one, that carbon's going to make 5 bonds. It's not allowed. We need to break a bond. Luckily, I have a good leaving group, which is O minus. And it's not even O minus because it's going to make its own carbonyl. And it's got a good leaving group, which is that one. So we number our arrows. This is the order we drew the arrows in. And what we end up coming off with at the end here is we get a acetone from the left-hand side here. We get ethanol from the right-hand side. And we get DMSO from the reagent that we added. This is sometimes just drawn as that. Both ways are correct. And so that's how we get to the end here, is we have this addition of ozone, this 3 oxygens to the double bond. They make this primary ozonide. The primary ozonide breaks apart because it doesn't want all these bonds to oxygen. Breaks apart into C. C isn't happy because it's charged, so it rearranges into the secondary ozonide, which is better than the primary ozonide because you have fewer oxygen-oxygen bonds, more oxygen-carbon bonds, which is good, but it's not particularly stable. So you add in a decent nucleophile that can almost, what we're doing here is we're basically oxidizing the nucleophile. We're basically reducing the secondary ozonide. We're eliminating off an oxygen and its electrons. And so we're using either dimethyl sulfide or triphenylphosphine. That comes in, attacks one of the oxygens, and the whole molecule falls apart to give us the 2 carbonyls. And so that's how we get to the end product.